So I will take it until 4 p.m. because I have another thing at 4:30.
Okay.
So meeting. So anyway, any doubts on whatever we discussed yesterday? Because I'll also make this interactive,
Yes.
and I'll go through the design process. Any doubts on whatever we discussed yesterday on the op-amp design?
Hello,
Any
participants.
participant or
We have started the session 2, and welcome to the session 2. And ma'am, please continue.
yes, participant or panelist, any one you have your doubts about the yesterday session that already Professor Shao has taken with an with a detailed interaction regarding the design of operational amplifier. So have you any doubt on it? So please either write in chat box or question answer in the chat box, it is better. Now you write in the chat box immediately so that we can get any questions you have. Shomo, you have? Hello? Hello? So I think
Yes, ma'am. Shomo is there.
Shomo is there. Shomo, have you any question yesterday on yesterday's session that Sarah has taken?
You may please unmute your mic.
I think the Shomo is not there. They are
He
waiting
has
for.
put something on the chat box. I would like to understand about the layout.
Okay. So layout session actually really we want, because layout in detail with background of like circuits and aspects and the parameters that to be design rule checking and everything we want to know also. So if you have that kind of.
Yes. So basically doing the layout, as I said, I would be using the my thing that I had done before, not layout Excel. So I will be giving you the techniques for layout, but I would not. The tool usage, I think layout Excel I won't give. I'll give from the designer perspective what needs to be done, and I will do the layout of the first stage, okay, and show how it needs to be done. So what I will do is, as I said, the layout I do it in a half circuit format. Okay, I believe you can see my screen, right?
Yes, sir.
Okay, so I will call file new and cell view. So I'll call it build op amp half. Okay, so this is, I'll build the half circuit of the op amp. Okay. Now let's see how the half circuit of the op amp first stage involves at least these transistors first. So I'll put these transistors first. So this is a 2 micron finger with 8 with total 8 microns, 4 fingers, and 5 multipliers. So the way I would do it is 2 microns. And is it an LV or is it a LV? Okay, so that means I'm going to instantiate LV. 2, 4. So this is what I'm going to do. And as I said, I will put in dummies. So one dummy on each side. So let's make it 6, this thing, and therefore 2 microns each. Okay, and then I have to make 5 multipliers. So 5 multiplier means I'm going to put 5 of this in parallel. Okay, so now what we need to do is we need to minimize the amount of gate resistance. So the gate resistance is minimized by putting contacts here, here, everywhere. You just put in the contacts. So I'll put the M1 poly contact, and let's say I put roughly 6 contacts. Keep in mind 4 of them are dummies. So it should be 5 contacts. Okay. And now this is a 5-finger device. Okay. And we should put all the contacts in the center also. So this becomes the input device. Now this is a 5-finger device. Now we have to define the 4-finger device. We have to define the source and drain of this. Okay. Now the source is let us say these are the fingers. This is one device. This is source and drain of the device. Then this is another device, source and drain of the device. This is third device, source and drain. This is the fourth device, source and drain. Right? So what I will do is I will connect them with metal tube. Okay. So I'm going to connect them. So now alternate, I'm going to connect this and this. I will define as the source. Okay. So this defines the source. Of one of the 4-finger device. Now we'll define the others. The drain will define it by connecting metal over here. So I don't think I can put two vias here. So usually it's a good practice to put 2 vias, but unfortunately the size that I've chosen, we cannot put 2 vias here. So I'll reduce all of them to 1 via.
Why put to have it two vias?
Because at least it is more reliable connection. If one of them fails, the other one will be there. So
Okay.
always a good practice to have two vias as much as wherever possible. Under extreme circumstances, you can put one via. So for demo purpose, I'm putting one via because chose the size of 2 microns to illustrate the finger and multiplier concept. So we right now do it with one via. Okay, so that is there, and then the other one also, now I have to define the drain. The drain will be nothing but over here. So the drain is one connection here and the other connection here. Okay, so now we have source. This metal 2 is acting as the source, this metal 2 is acting as the drain.
So how it is different from that layout, the advanced layout that you were telling, that it is somehow the conventional old type of layout?
No, it
Why?
is not. Only thing is that that is advanced in the sense that it will get the transistors directly into this. So I'll show you how it works. But I'm not an ex. I've hardly used it, so that's why. For example, if I launch, if I do layout X, sorry, not ADX, launch layout Excel. Okay, I'll say create new. Okay, configuration automatic. So what it does is it will do this. Okay. So what it does is it creates it puts in here. Now I'll click on this. If I click on this, it should, you see, that's why I have not used it that much. But actually what it does is it should bring in the transistor. It will bring in the transistor. So if I highlight this, then it will show that this is the thing. And if I copy this again, it will probably, okay, I'm sorry, I should not be getting into this because I rarely use it because I can manage with the older version. So what it does is it associates a transistor with this. Here I am manually placing the transistor. Okay, and I'm defining the source drain manually. The source drain get automatically defined, and all you have to do is make the connections. Okay, so now this is one set, one finger is this thing. Then I will connect the multipliers. Okay. So similarly, I can do all these connections, and then I will connect these metal tools because all the sources of these transistors need to be connected. So I'll connect all of them in this thing. Similarly, all these drains need to be connected. I will connect all of them using metal 3, and the gate will also be connected using this. So when you're doing layout, it is a good practice to define a convention. Odd metals could be going horizontally, and even metals could be going vertically. Okay, point number one. Odd metal means metal 3, metal 5. These will go horizontally, and even metals like metal 2, metal 4, and metal 6 could go vertical. That is one convention. And metal 1 can go either way. But in case of op amps, I do not restrict that. You can turn also the metals. Metal 2 can both go horizontal or vertical. Depends on what makes the layout much more convenient. Okay, so now let's say we do this connection, so all the input devices are connected. Next we bring in the cascode device. So next we'll bring this cascode device. So here it's a multiplier of 10. So it is 2 microns, 4 fingers, and then this side. Okay, so this is there. So I would rotate this like this, and it should be 6 fingers because I need dummies. Okay, so I will put them here. So instead of instantiating them one by one, so what I do is, since these are anyway 5 of them, so I will copy them. Okay, and I will change the property here for all of them to 500 nano. Okay, so this makes it 5 of them. We need 10 of them, so I will copy one on top of the other. Okay, this becomes the cascode device. Then finally we have to make the connections of the source drain. So that has to be done, and the gates have to be connected also, just like we have done here. Okay, then we instantiate this one. This is PMOS. So 16 fingers, and then this thing. So let's see. Instantiate E. So this is there. So let's see what are the dimensions here. 6 fingers, 32. So I have to make it 18 fingers and 5 multiply. So I'll make it 18 fingers because I have to add the dummies. Okay, and then I will put in the 5 multiplier. Okay, so now this is the PMOS. This is the cascode device. This is the input pair. Gates need to be connected, and keep in mind the dummies for the NMOS. This gate will be connected to ground. This node will be connected to ground, and we have to instantiate the appropriate dummy transistor in the schematic for LES. And for the PMOS, the dummy, this is a dummy transistor. This has to be connected to VDD so that the PMOS is off, and this node has to be connected. This source has to be connected to VDD. Okay. So you have this. So you can follow the similar guidelines for connecting the source and drains for each finger, and then you can finish up the connection of this half circuit. After this half circuit is done, then what you do is you go into the full op amp, and then here you instantiate that. Build op amp half. And then you mirror it, copy this, F3, you connect it over here. Okay. Now, this becomes the full op amp first stage, but you need to put in this transistor here. Now, keep in mind, this is a single finger device. If this were a 2-finger device, then I could have put it in the half circuit. Okay. So now I have to put this device and this device. So the way I would do it is, I would go into this, I'll do an in-place edit, and I will move these transistors upwards and put these devices over here in the center and appropriately bias it. Now, next thing that comes is the tail transistor. Tail transistor is 10 fingers, 10 multipliers, 8 of those. So let me insert now the tail transistor will come in here. I should put dummies. I will put the tail transistor. Since this was 10 finger, I could have also put this in the half circuit, each half, and then this. So this would look like the first stage. Of course, I have not done the routing because it is this routing takes quite some time. You have to put in all the vias and do all the routings manually. Okay. So now this becomes the input, this becomes the cascode, and then appropriately the bias circuit. Then this becomes the first stage here. And similarly, you can do the second stage. The output comes out from here, it goes to the second stage. It can be built like that. Now, this is how this, because overall, if I see, if I have to build this whole op amp and do a proper layout, it takes roughly 6 to 8 hours to really get this done with LVS and DRC clean. Okay. So now I will show the LVS flow for the op amp, that we have already built. Okay. So, sorry. Yes. So this is the layout of the op amp that we have already built. This has the compensation capacitor and everything. And this is the corresponding schematic. Okay. So I'll go into the op amp schematic first. This is the, so as I said, the dummy transistors that we have put, we have to put them appropriately in the schematic. So now this is the layout. So we have this overall layout. I think it took my student roughly 2 days to finish it because we had to make sure that matching and all these things are properly done. Power routing is optimally done and all. So overall, this is how the layout looks like. You can see that it is exactly half circuit layout has been done and all the connections have been appropriately made, right? So now, any questions so far on the layout? Because to do that layout right in front of you, it takes quite some time. So I showed that initially you do the half circuit, instantiate the values. So here, this bias transistor, cascode bias, we had 2 fingers, luckily, even number of fingers. So we could split it up into half circuit, right? But in the other case, we did not have it. So we had to do a separate one. Both half circuit did not contain the bias circuit. Okay. Any questions?
Yes, for a metal line, you were telling something rules regarding conventional that you were telling, but I cannot hear. That you were telling that odd metals are horizontally to be connected and even metals.
No, basically, usually when we are doing routing, a convention needs to be decided before you start the layout. So it's now up to you. I mean, it depends on, varies from person to person. So I say that or even metals can go vertically and odd metals can go horizontally. Okay. And metal one can go either way because metal one is used for local connections.
Oh. So for local connection, that connection may be in anywhere, but which are in the globally, that means if it is like supply and others.
And signals also. You can see that here, for example, metal 2 is yellow, it is going vertically always. I followed that convention. Metal 4 is also even, is this purple line. This is going vertically. And metal 3 is odd. It is going horizontal.
Okay. So that means these metal layers are different metal layers that
Right.
are connecting in between layers maybe.
Yes, 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 yes.
Yes. And those who are horizontally, these are locally connected.
No. Metal 3 is horizontal. So metal 3 is odd metal layer. So that is why it is going horizontally. We have chosen the convention. And 2 and 4 are even metal layers, so they are going vertically. So if you see here, I will just show the metal 3, metal 2, let's say. So you can see that metal 2 is going vertically. Okay. Then I'll show metal 3. You can see that metal 3 is going horizontal. Okay. Some cases, little bit we are making it vertical. Okay, for short connections, that is fine. Okay. Now, then metal 4, you will see that metal 4 is going vertically. Metal 4 is going vertically here, but because I'm doing a global connection here for power delivery, I have done it in this manner. Okay, but otherwise we try to follow this. In analog also, in analog layout, although we set the convention, sometimes we can violate the convention to meet the power delivery or other critical signal constraints. So, and metal 5 is not used in this except for the capacitor. The MIM capacitor is metal 5 and metal 6. So that's why. And metals.
Metal 5 and 6? Which capacitor?
Are in the MIM capacitor. MIM. The MIM capacitor is realized using metal 3, 5 and 6.
Why they are used?
No, because that is the MIM capacitor design that the foundry gives you.
Okay.
The MIM capacitor realizes the capacitors, the foundry realizes MIM capacitors using the top metal layers. Top 2 layers, metal 5 and metal 6.
MIM means MIM that you were telling.
MIM, yes, exactly.
MIM, yes.
MIM capacitor. Metal insulated metal.
Yes, yes.
So Soumya has raised the hand. So
yes, actually, I want to ask that initially when you extracted the layout from the schematic, then have you detached the terminals?
when you detach, okay, now we'll go into extraction. So now he's getting to the point. So let's suppose the layout is over. Okay. So let me go through the flow. After the layout is done, we need to do DRC. We need to do LBS, layout versus schematic.
Can I just see the VDD and the ground terminals? I mean, are those are the common terminals from which you have connected the source and the drain?
In this one, here?
Yes, yes, yes.
Yeah, so now let us see. So this one, here, VDD is connected to the source and this drain is connected over here, right? So that transistor is over here. Okay, so this is the drain. This yellow connection is the metal to drain and this is the VDD connection. You see this different color, this VR? This is VDD. This is VDD, VDD, VDD. Does it make sense?
Okay.
What was your question?
Okay, I just want to know about the the terminals from where you have connected the VDD and the ground.
Terminals means what? Which terminal are you talking about?
The VDD one.
VDD is this one. This metal line is VDD.
Okay, okay.
This metal line is metal 4 is VDD. See, A VDD is labeled here.
Okay.
Ultimately, this will be connected to a pin. That
will be connected at the chip level. This is a block level layout we are doing.
Okay, okay. Now we are doing the block level.
Okay.
Yes.
Does it answer your question?
Yes, yes.
Okay. So now, in order to do DRC, we use Caliber, which is a metal graphics tool, and it is the industry standard tool. It has never given problems in my industry tenure, and post my industry tenure also. I have seen a lot of people say that Caliber works beautifully. Okay.
Caliber is the open source tool?
No. It is most expensive tool.
Oh, it is
So
from.
It's from Mentor Graphics. Okay, and Caliber Mentor Graphics sells Caliber, and it is one of the best tools for DRC, LVS, and extraction. Okay, cadence is nowhere near close to it. Okay, that is, and everybody follows this thing. Although cadence is trying to come up, and the latest cadence extraction tools are also good. But I personally prefer Caliber because I've been using it for last 15 years, and I never had a problem with Caliber in all the tape outs that I've done in the last 15 years. I've been doing tape outs through Caliber, and the first 5 years of my life we did tape out through during my industry tenure we did tape out through Hercules. It is a synopsis tool that had issues, a lot of issues. So I don't think Hercules is there anymore. I don't know if it is still there. So 2000 to 2005 Hercules was used, but I'll show how the Caliber DRC. So we'll run the DRC first here. Okay, and you load the DRC. So basically you define the rules here. This is different from Ashura DRC. Okay, Ashura is cadence thing. If you are planning to buy cadence, you will get Ashura DRC.
Sorry to interrupt, but when earlier when I was designing the any layout for any basic kits in layout Excel, shouldn't I go for Ashura and then run DRC?
Why we always do it using Caliber. It doesn't matter. I use Caliber because I am very comfortable with it. That's my only thing. Ashura, with Caliber I can debug also. If there is an LVS or DRC issue, I can easily debug. Ashura I have not used much. So it's just a personal preference, and I like Caliber more than Ashura. Okay, so you define the rule files. So you can see the rule file, Caliber rule file looks like this. Okay, you don't need to understand what is inside because this is generated by the foundry and given to us. So we can use this rule file, and then you have to tell, okay, it has to take the input, you have to export the layout. Okay, then it will give you DRC options. This, do not do this option. Connect nets with a colon. It's a very risky option. People have done this and their chip doesn't work because they thought that the connection is there, but in reality there was no physical connection. So it was a connection by label. So this is not a good option to do. Then I think then you just run the DRC. Okay, then it pops this up and it gives you all the violations that are here. Okay, for example, we have a density violation. Okay, VR density, all these density violations are there. Density violations are fixed before the tape out, so we don't fix it. Any other violations need to be fixed. So if you see, we'll have mostly density violations in this because this design has been done, so this is working. So you will see density violation right now. You won't see any other violation in this design. Okay, so this is the die corner rule because we are doing full chip DRC. So it thinks that this is the full chip and it does not have a corner, so it flags these errors. Okay, so these we ignore it because that is not required for block level DRC. Okay, next thing is you have to go into LVS. I also prefer Caliber LVS because I can debug it with ease. So similarly, LVS also you pick up the there is a rules file. So that this is how the rule file looks like. Okay, and you define the input. Make sure that the layout export is enabled. Netlist is also enabled. Okay, you define the power and ground nets in the LVS options. Otherwise, it will say that power and ground do not exist. So it is better to define all the power and ground nets that is there in your system. We had a multiple power supplies and multiple grounds. Okay, so we purposely did that. Now then you run the LVS. Now this is very, very technology specific. So whatever you learn here might not work out. So might change with 28 nanometer, there are other issues. So, you have to figure out in the technology the issues of LVS and DRC. Okay, then only it will make sense. So now here you see that this was clean, so it gives you a smiley face. Okay, and it tells you exactly all the nets and everything that it has matched, and everything is clean here. Okay, And it should give you a green symbol here. If there is a warning, please try to avoid any warnings. Warnings are not good. Only software guys can ignore warnings. Hardware guys cannot ignore warnings. Okay. Never try to ignore any warning in hardware design. Software guys, software you can ignore as many warnings as possible. Okay. So now we have done this. Now I'll get into the extraction. Okay. So extraction, since we do not have the caliber rule deck for extraction, we'll be using the cadence rule deck for extraction, because UMC did not have the caliber rule deck. We do not have it with us. We will be using the Ashura. Now Ashura, for extraction to work, you have to run the LVS first using Ashura. So you go to Ashura and you run the LVS. Otherwise, because from the LVS netlist, it will start doing the extraction based on that. So you have to first run the LVS on Ashura, okay? And in the LVS for Ashura, you have to define the Ashura rule files. Okay, these are the rule files for Ashura. For every technology, you have to talk to the technology guy to set this up for you. Or if you know how to set it up, you can do that. So sometimes in 28 nanometer I had issues, so I had sent an email to Europractice, and then they told us to do certain changes, and we did that, and it worked LVS and DRC for us. Okay, so now I'll do this. Okay. Okay, so it runs it is running the LVS first, and it says that it is clean. Okay, so I would not look at the log file. So LVS is done. Now we go into Ashura Qantas QRC. Okay, so here the one important thing is that there are various forms of extraction. So if you note it down, there is R only extraction, C only extraction, RC extraction, RLC, and RLCK. 180 nanometer does not have inductor models for RLC extraction. Okay. I'm not sure what is RLCK, so I don't know about that, but RLC is resistor, inductor, capacitor extraction. So we mostly do R only, C only, or RC extraction, depending on what aspect we want to look at. So let us do a C only. Now C only has two flavors. Okay. One is coupled, other is decoupled. Okay. Third is decoupled to substrate. Okay. So now let's see what are the meanings of those. Coupled. Okay. Coupled means it will find with respect to each other. There are multiple nets. For example, if you look at this thing over here, this metal line is parallel to this metal line. So when I do coupled extraction, then it will extract the capacitance between these two. Okay. If I do decoupled extraction, then it will extract everything with respect to ground. If I do decoupled to substrate, it will extract each of these nets with respect to the substrate. So there is a substrate, there is a ground, and there is finally a coupled extraction. Now, you might ask, what is the difference between coupled to substrate and coupled to ground? In RF design, we usually put a ground plane, which is the metal plane, right? And if I do an extraction decoupled to substrate, then it will ignore the ground plane and extract all the nets with respect to the substrate, which is the substrate-based silicon wafer. Okay. If I do decoupled, it will then decouple, and it will do it with respect to the respective ground. Okay. And ideally, for precision simulation, I think you should do coupled. Now, why did they give these three options? Because precision simulation is best, right? The coupled netlist will be much bigger. So simulation time will be smaller, will be larger. Okay. So depending on what aspect of the circuit you are looking at, please choose your extraction deck appropriately. Okay. If you want to simulate how, let's say, now what are the different things that we have to look at? So you might want to run, I hope you wrote down all these cases. R only simulation extracts the resistance of all the nets. Okay. C only capacitance it extracts. Now C only has three favors: coupled, decoupled, and decoupled to substrate. Am I clear with that? Is that okay?
Yes. And similarly, when you are transistor to transistor coupled also, then also the same thing that we can use it. The coupling means here the two transistors are actually influencing one another.
No. This coupled and all are with respect to the wires only, with respect to the nets. Transistor will get extracted as a transistor.
No, when the two transistors are coupled together, that is the coupling capacitors and other things are when they are in the layout portion. That means they are also we can couple or decouple it by.
No. Transistor, there is no coupling. It is only the wires. When extraction, it only extracts the wire.
Okay. Yes.
It
Yes.
does not extract anything else. It extracts the
Okay.
transistors also, but
That is the layout is only for interconnects and wires.
yes, exactly. So please all of you write down capacitance. There are three flavors of extraction: coupled, decoupled, and decoupled to substrate. Okay. Next thing is after that there is RC. RC means it will break a wire. This wire will be broken into smaller resistor capacitors like a pie section. It will break it up and extract the netlist. Okay, all the wires will be broken down into smaller resistor capacitor. So now let us see what is the size of the netlist for each of the cases. See only with decoupled and decoupled gives you the smallest size netlist. Okay. C only with coupled gives you moderate size netlist. R only gives you little more than moderate size netlist. Okay. RC gives you the largest netlist. Okay. Now, what are the repercussions? Largest netlist means more simulation times, more nets, more variables to be saved. It takes a lot of huge disk space. So we have to be optimal in terms of doing that. Am I clear? Okay. So now let me now what happens is that once we extract these different flavors, we save it in this format. We call it as AB extracted C coupled, AB extracted DC coupled, AB extracted R, AB extracted RC. Okay. So now let's look at AB extracted R netlist. How does it look? It exactly looks like the net layout, right? But it will have small resistors there. You see a resistor here? $789 milliohms resistor is there. So it will have the layout and it will put in the connections based on resistors. You see these resistors? These are all extracted resistors. And of course, it will put the transistor wherever there is a transistor also. For example, here there is a transistor. So let's zoom in and find out where the transistor is. It is so, let me remove. I'm not able to find where the transistors are. So it has extracted the transistors. It's just that I'm not able to find where they are. So it has extracted all these components, resistors and all these things. Okay. So now this is an R extractor. Now let's look at the RC extracted. It will also look like the same. okay, but it will have
Capacity.
R's and C's. See, this is so small that it's very difficult to zoom in. So you can see that P resistors are there, and P capacitor transistor is here. Finally, I found it. Okay, somewhere in between it is there. Here is a transistor. Okay, and PLV, and there will be capacitor also. So we have to find that out. So it will have capacitors and resistors. Okay, so is this a capacitor? What is this? Okay, I don't know. So anyway, so there will be resistors and capacitors. Okay, so you will so depending on the type of netlist, it will accordingly extract it. So let's say C coupled. Okay, so we'll see this, and this will have resistors and capacitors. So see, transistor is here, and capacitor is here. Okay, you see that? So all the resistors and capacitors are instantiated here after the extraction. Okay, that's what the tool does. Now, after you have extracted it, now we have to run a simulation. Okay, now the simulation should be run in a manner that it should you should be able to sometimes simulate with the schematic. So we have all these things, right? We have the schematic, we have these different views of the extracted netlist. Okay, so I should be able to view with all these different flavors and compare the performance of the netlist. Okay, so now let us see how will I. So now please notice this carefully. So am I clear with respect to the extraction views? What are the different views and when to extract and all? And how does the extracted netlist look like? Any questions on that? Before I go into this, how to simulate using those extracted netlists?
Yes, actually the capacitor value that you have extracted, are those the parasitic capacitor?
Parasitic, those are wire capacitors. Extraction
Okay.
only extracts the parasitics.
Okay.
There's it will put in the transistor, but the transistor is same as the transistor in the schematic also. You got my point, right? Extraction creates a netlist which has the same transistors as in the schematic, but adds in the parasitic capacitors and resistors due to the wiring. Is that clear?
Yes.
Okay. So now we'll we built the layout. Of course, the layout will take quite some time to make it fully connected and fully look nice and all. I showed you how we started off with the half circuit, put the 2 half circuits, okay, and got the full layout, although it is not LVS. So then I showed the layout that was done already, okay, and then after that, keep in mind, op-amp layout cannot be done in one go. When I said that layout took 2 days to do the full layout, we had to do multiple extractions on that thing to finally converge on the final layout, because we have to extract and make sure that everything is perfectly matched and all. Okay, so after so that means we did that. Then we go into DRC, we go into LVS, LVS first, then DRC. Once it is LVS and DRC clean, then only we do the extraction. And extraction has multiple flavors: R only extraction, C only extraction. C only has 3 flavors of it: coupled, decoupled, decoupled to substrate, and then RC extraction. So these are different flavors of extraction. Which flavor to use depending on what you want to see in your simulation. Okay, why not use always RC? Okay, yes you could, but the problem is that your netlist size is so big that it takes a long time to simulate. But I want to see whether current is flowing properly or not. How much is the drop in the wire, voltage drop in the wire? For that, why do I need to do an RC extraction? An R only extraction will do that purpose, right? So it all depends on. Now if I have a very low frequency circuit, right, biomedical circuit, right, why do I need to do an RC extraction? A C only extraction is good enough. So these are some judgment calls that a designer makes based on what is the design spec. Okay. Now, now I'll go into how to simulate it. Now, simulation is done by using something called file. So I'll create a new test bench file, new. Okay. a cell view, and I'll call it as a test bench op-amp. TB underscore op-amp. Okay, and I will create a config view. Keep in mind, this is very, very important that we have to create a config view. Okay, so I create this, and here I will say that view I will use schematic. Okay, and I'll use a template here, use template, and I'll use something called Spectre template. Okay, so use template, Spectre template, and then click OK.
Yeah.
Okay, so now I will open the
We can directly select the test. I mean the from the test circuit, right?
Not really. So then I'm also going to create something called file new cell view. I'll create a schematic here. Okay. So in this schematic, I'm going to instantiate the symbol for the op-amp. So I instantiated this symbol. Okay. I have not put any labels, so that is okay. Then I can do the save. Okay. Ah. Okay. So now you see that I open it, and what we have is, this is the schematic view of the test bench. Okay, I have instantiated the op-amp 2 stage, and here I am this schematic. You can see that view found. These are the various views. Now this is what I can do. I want to simulate this. This is a test bench that I want to simulate. If I want to simulate this, then what I will do is I will set the view, instead of setting it to schematic, I set it to the extracted view, the whatever view I have for this. Okay. Suppose I want to do an R only extraction, then I'll go in the here. I'll go here, view found. Right click on it here. Right click on it, set cell view to AV extracted R, and then you save. That automatically everything else goes, and you have the AV extracted R view. So now if I go into this, automatically it will take me to the AV extracted view R, which is okay. So that means when I am trying to simulate this, I will now simulate this. That means it will use this view, the extracted netlist, and I'll get the performance based on the R extracted. If I set the cell view to, C coupled, then it will use the coupled view. So you can see that it will go into the C plus C coupled view. Okay. So now this is how you use the config view to do the simulations after you have extracted it. Am I clear? Any questions?
Yes, understood, sir. No.
Okay. So since we have done this, so this kind of wraps up the full. So we did ERC, LBS, extraction. Okay. Then simulation based on extraction. Okay. Now let me show you something interesting here. Okay. So let me pull up a test bench of let me copy everything. So I will now simulate right in front of you. But what I will do is I will look at the DC simulations. Sorry, I'll run a transient simulation. Okay, and I'll show you how I'll use the R only extracted netlist, and I will show you how the power delivery, how good is the power delivery to the overall system. Okay, so I'm going to use the AB extracted R. Okay, now I'll do launch. Okay, so session load state, and I will load it from one of the, I think here I will just load some arbitrary state. So this, and I'll add a transient simulation for 1 microsecond. Okay. Okay. So CL is 1 pico. I'm setting the load capacitance. V common mode was 900. VCM1. Let me see what is VCM1. So VCM was 9600. Let me send it. It's okay. 900 VCM1. 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 I set it to 1.4. Okay, so now this is what I have set it to. So I'll just fire the simulation. So I believe I'm finished. Now, this is the R only simulation. I ran the simulation. Now you will see how many power net, the resistance of the power line VDD and the ground line have been broken into multiple nets because it is the R only extracted simulation. So I will see how bad is the power delivery, means how close is it to ideal. Okay. So I'll go to the tools results browser. That's the only way you can see, and transient this thing. So I will search for VDD. So you see that there are multiple VDDs here, and there are roughly, if I select all of them, this is the power supply. So what are you seeing here? I gave a 1.8 volt supply, but current is flowing in the circuitry. Okay, and current is flowing through the power line, the wires. When current flows through the wire, what happens? The wire has resistance. What will happen? There will be a drop in the resistor. So the power is not exactly 1.8 volts. Okay, so you can see that we have some amount of drop. We have roughly how much? 48, 795 5 millivolts, 4.8 millivolt of drop from 1.8 volts. Am I clear? Does it make sense?
Yes, sir. Yes, sir.
So now for this, in order to see how is the drop in the power line, I need not run an RC simulation, because capacitance does not cause a power IR drop. This drop is called
Yes.
the IR drop. Okay.
Yes.
So now let me
So we can only
delete all
select
this.
the register and we can see the drop.
Sorry,
We can only select the register, right?
I am not selecting the resistor. I am selecting the resistor only netlist.
Okay.
R extracted netlist. You can see that AB extracted R netlist. I am not doing the RC extracted, because why should I simulate an RC extracted netlist which
Only
is
for
much
the
bigger than an R extracted netlist? You got my point, right? So that is why we'll see the VSS also. How is the power drop in the VSS? Okay, so we will now look at how is the VSS. So you can see we gave only one VSS, but because you can see that VSS gives you almost 11 millivolt drop, 10.6. Ideally, it should be 0, but I'm not getting this. So when you are doing this analog layout, 10 millivolts is a lot of drop actually. But for us, it was okay, because we made sure that it is 10 millivolt drop here and 5 millivolt drop there. Okay, on the top side VDD. So our circuit will effectively be getting 15 millivolts less than what it was supposed to you get. But we cannot afford to have asymmetry between the grounds of the different nets. Means this ground and this ground, there should be no difference between them. Okay, and this becomes clear when we see, we will plot the output P and output N. You will see that output P and output N, they will almost be similar. Okay, so we'll show that. Okay, so actually let's get output. So oh, there is S1 output, stage 1 output is also there. So we'll ignore the stage 1 outputs for now, because I'm interested in the final output. And there are hundreds of such nets, because as RC net, R only extraction splits up that line into a lot of lines. So that's why it is difficult to find out where is what. So it is, we just plot everything and see what happens. And we try to make sure that they are equal. So there is still one more. So you can see that, oh, probably some bias voltage somewhere I messed up. So some voltage is not properly set. So that's why we are getting this 200 millivolts, but that's okay. So now I look into out N. Okay. And I will plot all the out Ns and remove the stage 1 output N. Okay. So now I have to remove all the stage 1 output N. So now you see that both out N and out P, they are almost together. There is hardly any mismatch between them. They are both sitting very close to each other. Okay. If you want, what you can do is you can you can create a new sub window. Okay. And then I will move all the out ends to that window. Okay. Now, do you see that both out N and out P are in the same range? This clearly shows that our circuit power delivery is perfect. If our power delivery is not perfect, then this and this, there will be a difference between the two, out N and out P. And this getting them equal, when somebody is doing the layout in first go, he does not get it. Even experts do not get it, those who are in the industry. So it needs at least 4 or 5 times to refine the layout of especially op-amp before we get to this point where there is hardly any difference between the two due to, and that means the power delivery to the supply and ground is perfect. Okay. Does it, so now this is one of the smallest and simulation this is a simulation. We saw that it runs very quickly and gives us a lot of information to show how is our design, how good is our design. I have never seen a lot of people do not do this simulation, right? In industry, you cannot build a chip without doing this kind of simulation. So please keep in mind, these are some small simulations that are very, very important. How balanced is the output of the op-amp? Okay. And especially if the op-amp gain is very high, then you have to make sure that they're perfectly balanced. Okay. So with this, I think if there are no questions, I'll wrap up the op-amp layout aspect here. How we went from layout, DRC, LBS, extraction, different forms of extraction, creating a config view, okay, and then using the right view in the simulation to do the simulation. Any questions so far? Any questions? If no further questions, shall we move to the digital layout? Or-
Okay, sir.
Yes, sir.
Okay, so then I'll move into standard cell layout. Okay, so all of you noted down about the config view, different forms of extraction. So before I go into that, so let me open a so do you guys already know about standard cells? How they're designed? Any knowledge? You already have some prior knowledge, or so? Do you know what is invex 1, invex 2? Do you know what these are? What is X1, X2, X4,
Yes.
X8? All of you know
Actually,
about
those
it.
are the inverter with drive strength 1.
And what is
The first one.
X32?
I mean, we are connecting the inverters, right?
Now, what is the difference between inverter X1 and X32?
The drive strength will be more, I guess.
Okay. So basically it is the drive strength. So we build our own standard cells. So this is our own standard cell built by my students. Okay. So I'll start with an inverter X1. So the schematic of inverter X1 is actually inverter X1 uses minimum size transistor. What happened? It's not opening. Okay. So this is the minimum size transistor. In case of 180 nanometer, it is 440 is the NMOS and 840 is the PMOS. And typically inverters in digital gates, always the channel length is minimum. Okay. Now what is INVEX 2? INVEX 2 will have exactly the twice the sizes. 840 and 1.67. Well, I would say exactly twice the sizes. Okay. And what is INVEX 4?
It will be 2 times that of
2
the
times the X2. So two fingers of X, 840 and
yeah.
2 fingers of NF is 1.6.
Yeah.
Now that
Actually, when
is,
I was designing the inverter, I have set the width of PMOS to 850 nanometer, and is 2 times will be for NMOS. It will be 1.7 micrometer.
why should NMOS be bigger than PMOS?
Sorry, I just said the opposite actually.
Okay, no, usually inverter X1 should be the minimum size device.
Yes.
Okay, and then the X2, X4 can be different. Okay, now if inverter X1 is of this size, a 440 and 840, what should be the sizes of the NAND gate X1?
Will it be 1.275
No, it is
micrometer?
one. Let's take this. You see this. This is 440 nanometer. What should be the size of the NAND gate? NMOS. And what should be the size of the NAND gate PMOS? Okay, so I'll show you that, and then you tell me the reason why it is like. Okay. Now tell me, why is this 840, not 440? And why is this 840, not half or whatever?
Because of the series or parallel connection.
Yeah, but when you have series connection, why does it increase? So it increases because the resistance has to be appropriately decreased. Have you, do you guys know about logical effort, electrical effort and all? All of you?
No, sir.
Oh, then I don't know how to, because without logical effort, a logical effort of an inverter is 1. So how, okay, anyway, so let's go into the layout aspect of this thing. So you just scale this up. So unless, see, the standard cell design cannot be done unless we know the sizing strategy. How is the NOR gate? So NOR gate, if you see NOR X1 is, what is the size here? It is 440, same as this, right? But what about the PMOS? It is 1.68. It's 4 times bigger than this, right? So any reason why it is like that? You don't know, right? Nobody knows. Okay. So anyway, so let's assume that we have sized it correctly. Now let's see how do we. Now, what does this sizing strategy say? That the NMOS is half the size of the PMOS. Okay. And the layout of the standard cell is done in a manner called, it has to be called defined by number of tracks. Okay. What is the meaning of number of tracks? How many metal lines can be routed between the VSS and ground line, where VDD and ground line. So standard cells have two rails, VDD rail on the top and ground rail on the bottom. Okay, so that is there. So you have VDD rail and ground rail. Between these rails, how many metals can be routed? Okay, that means how many metal twos can be routed, how many metal threes can be routed, because finally the routing has to be done by the automatic place and route tool. So that means you have to tell exactly how many track cell is this, and the place and route tool is going to route along these along those tracks. So you define tracks here which are not really defined here as such. The tool automatically picks it up once it sees this and this. Okay, so that means if I have to make NAND inverter 32, that means my height of the standard cell is fixed. Height cannot be changed. Height of the standard cell is always fixed. Okay, that cannot be changed. That is defined by the number of tracks we can take. Now, if I have to build a X64, what happens if the height is fixed? We increase it along the X direction. So this height will not change. So all standard cells will always have the same height. Okay, in all technology nodes, and the connections we will appropriately do this thing. So they will have the same, the Y height will be the same, and the X direction will keep on growing. For example, the D flip-flop. So I'll show you the D flip-flop. Oh, I don't have the latest one. So that's a problem. Okay, I'll show you the XNOR. This is the XNOR gate. This thing. Oh, I don't have the actual one second. Let me just put this out. Oh, so we have the set preset. Okay, so that's how we do. Okay, so yeah, this is the actual one. So we did not do the D flip flop. We did the SR flip flop, set reset, because that's what we used. Okay, so this is the set reset D flip flop layout. You can see that the height is the same always. Only thing that happens is that the thing changes in the X direction. Okay, so you decide on the height and you do the connections. And another important thing, you can notice here, I am not using any other metals other than metal 1 for routing. Okay, you can see that there is no other metals used here other than metal 1. So it is a good practice to do all standard cell layout using metal 1 only. Okay, do not use any other metals. Okay, that is next thing. Now, how do you build a custom digital design using standard cell? I'll show you our clock driver. Okay, so our clock driver, calibration engine, all these things are digital logic. So I'll show you what is our. This is our clock driver. Okay, this is our clock driver. You can see that it is a bunch of OR gates, NAND gates, inverters, and all these things. Okay, and similarly the calibration engine is also this is the, okay, so this is a ripple counter here, and this is a bit so you can see that this is a ripple counter. So you have, again, it is built of set reset flip-flops. Okay. So now we have to build this clock generator. Now, how do you connect the standard cells? Okay. The connections of the standard cells is done by, so you can see that you decide, so this is, I will get rid of all, routing is done in other layers. So this is our standard, all the standard cells are here instantiated here. So what we do is we put the, you connect it. So I will show a demo here. Suppose I have to build, I'll do a layout here, file new. Okay, so I'll start doing layout using the standard cell. I'm doing some things, suppose NAND 2x1 I'll use first. So what I'll do is I'll first instantiate this. Okay, then I will instantiate a D flip-flop, let's say. SR. Okay, so I will connect them exactly side by side. Okay, then I'm going in the X direction. Y direction I have not increased. So what do I do if I have to go up in the Y direction? So I will instantiate, let's say, NOR X4. But this is VDD and this is VSS. So I cannot short it. So what will I do? I will flip this.
Can we invert?
Yeah, I'm inverting it, see. Okay, VDD now. So this is the ground rail, this becomes a VDD rail, and this becomes a VSS rail. And that is how you keep growing along in the Y direction. Okay, so you keep growing in the Y direction, and that's how you do build up the full layout. Does it make sense?
Okay.
Okay, so a few things about, now please keep in mind, please take a note of the standard cell, how it is done. So you start out with inverter X1, X2, X4, then similarly NAND X1, X2, X4, NOR X1, X2, X4, then flip-flops, XOR, XNOR. You can do other gates also. The layout, the power rails are split up by, this is the power rail, VSS and VDD. The distance between the power rails is decided by how many tracks of metal 2 can be routed between these two tracks. Pointer. If it is routed, if 10 tracks of 10 metal 2s can be routed, for example, let's pick M2. So that means I should be able to route 10 metal 2s. So this is 6. We have done it in 8-track one. This is an 8-track layout. Okay, so the spacing has to be increased because I just did it. So spacing should be as per design rule. So this is an 8-track design. Means 8 metal 2s can be routed in between the VDD and ground rails. Okay, so first of all, that is there. Now, the NMOS is half the size of the PMOS. That means this space between the ground and power rails have to be given, 1/3 of it is given to the NMOS. NMOS is here, and 2/3 is given to the PMOS for layout. Use only metal 1 and poly for all interconnections. Use only metal 1 and poly for all interconnections. Do not use higher layer metals.
Yeah.
As much as possible.
Yeah, and the green one are the wire, right?
Sorry?
The green one, the box from where you have interconnected the metal line and the poly.
This is the poly contact. Poly contact.
Yeah, yeah. Okay. Yeah.
Okay. So do not use metal 2. So basically you define on the number of tracks that defines the spacing between the power and ground rails. Rule number 1. Since NMOS is half the size of the PMOS, allocate 1/3 of that height to the NMOS layout and 2/3 of the height to the PMOS layout. Okay, for rule number 2. All the interconnections have to be done using metal 1 and poly. Do not use higher metals. Go use higher metals only if absolutely necessary. The height of the standard cell stays the same for all the gates. You cannot change the height. Therefore, the standard cell grows in the X direction. When you have to stack standard cell, you have to stack it so that you do not have any spacing. So I have overlapped the VDD, I have flipped it and connected it. Okay. Now you have to design different flavors of inverters and NAND gates. Now X1 is the minimum size. Then X2 will have twice the drive string. And you keep on increasing the size of the transistors like that, size of the gates. Any questions on the standard cell layout?
No, sir.
So I'll tell you one of the complex block that we have done. So one of my students did that. It's a second order digital delta sigma modulator. Okay, full custom design. Okay, so I'm trying to find where that is. Here. This is the delta sigma phase log view. This is the digital block. Okay, MASH. It's a completely full digital block. Okay, this is a MASH 111, which is a bunch of adders. Okay, so now if you look at the layout of this, this is the full MASH structure, right? This is the MASH V1 mux. So this is MASH V1 mux. So where is MASH? This is the one. So this is a complete digital block, and you can see how complex is the layout. Done fully using standard cells. Okay. Full hand drawn using standard cells. We did not use place and route tool for this. Okay, so this roughly took him 2 weeks to build this, including schematic, simulation, verification, and everything. So the amount of effort required is quite a bit to do that. It is not that straightforward because a lot of interconnections. So if you see the amount of interconnections, so the interconnections happen in metal 2, metal 3. You can see how much interconnections have been done. Because standard cell doesn't use metal 2 and 3. So all the interconnections are done using, and you see that these are the tracks between the VDD lines. And if you see the power lines are here. Between the power lines, the routings have been done. This power and ground lines are over here. Ground, power, alternate power and ground lines. And then final power delivery is done using metal 6 and metal 5. Metal 5 is used to do the power delivery. So if you see, the final power delivery is done here. And we have put the labels VDD, VSS, VDD, VSS all. Okay, so I hope this kind of clarifies the overall standard cell design and all. Any questions on this? So if there are no further questions, I don't think I have any more material to cover. I've gone from op-amp design, extracted layout and all, and then the standard cell aspect I have shown.
Hello?
I do not have any further material, so probably we can stop at this point if that is okay.
Am I audible? Hello?
Yes, yes, yes.
Yeah. Okay. So the previous layout which I have shown, that is very complex. Uh,
This one.
can you please get the previous one? Yeah, this one. Yeah.
Okay.
So it's very complex for me. So can you please tell? I mean, how you have adjusted the height and the length like the previous one along the x direction?
No, this is a bunch of standard cells here. So this is
Okay.
a set flip flop. Then something else is here. I don't know. I have to get into this. So this is all standard cells on the side by side and stacked up like that. So I did not understand your question.
Okay. Actually, I was trying to understand. I mean, if whether you have adjusted the height or along the x-axis like the previous one which you have shown. So these are directly the standard cell, right?
These are standard cell. You never adjust the y height. Y direction height is constant. X direction it has to increase. There is no other option. You cannot keep both direction this thing. Now, when you do the full layout, you want a square aspect ratio. You have to do floor planning. You have to see how many of them you can put side by side, how many you put on top of it. So that takes some time to iterate and all. It doesn't get done in one go. The full big complex layouts do not get done. So you do some blocks and then think about how to floor plan and partition it all.
Okay, sir.
Okay. So if there are no further questions, then I can stop at this point. I hope there was some learning that happened. So can I'll then it's 20 minutes early. So is that okay? Hello. Okay. So participants, attendees, there are no questions from anyone else, right?
Hello.
Hello. So I think I'm done with all the material that I wanted to cover. I did the standard cell also, op-amp, all the design. So I finished it a little early. I don't have any further material. If there are no further questions, can we wind up the talk?
Thank you so much, sir.
Thank you.
Participants having any doubt or any question, please ask.
No, actually, I don't have any doubt. Thank you, sir.
Okay, so all the best. I hope to see you guys after in person, all of you later when things come back to normal.
Yeah, and one more thing, sir.
Yes.
Actually, if I have any further problem whenever I design in the tool, can I ask for your help?
Yes.
Okay.
Yeah, you can always shoot an email and then I'll try to look into it. My students are already trained. They have done 2 tape outs.
Okay.
They can also take up without any issues. So my policy is nobody graduates without doing 2 tape outs. Nobody gets a PhD without 2 tape outs. So 2 tape outs is good enough to make sure that they know the whole flow.
Okay.
So not only this, they also do, students also do this, what do you call that, PCB design also. So I'll show you an interesting PCB that one of my student did it. Yeah, so let me share the screen. Can you see my screen?
Yes, sir.
This is the PCB. Bhanu is the student. This is a PCB, 50 ohms matched lines, high frequency PCB with, this is the PLL unit that I just showed. This is the top layer. This is the bottom layer. and the schematic and all. Okay, so the IC design work does not stop at just cadence level things. It has to go up to the PCB because the chip has to work fine. So you can always ask questions, okay, and I'll try to help you in the best possible.
Okay, thank you, sir.
Okay, okay then.
Thank you. Thank you, sir.
all.
Thank you very much.
Thank you all.
We have you for last some days. It's a great pleasure. We have learned a lot of things from you, and not only our students, our university affiliated college professors, they learned a lot of things. Thank you, sir. Thank you very much.
So just out of curiosity, so let me find out the attendees. Where Soumya, which college are you from? Which university?
Actually, I'm from the same university, the MAKAUT University, and from the same department who are conducting this program.
Okay. And Orijit, they? Sorry, I'm calling out for lack of better things. So Orijit, they, then Avali Banerjee, then Debolina Pramanik, Humayun
So,
Rahman.
Debolina Pramanik, they are from all are from MTech MAKAUT in microelectronics and VLSI department from.
I see. And Humayun Rahman, Noor Nabi Khan, Rudradeep Das,
So,
Samarjit
attending
Mal.
response, sir is asking something. Please response.
So before I wind up, I should at least know who
Yes.
all attend. Yes. Who is speaking? Please introduce yourself so that I get to know you.
Sir, myself, Dr. Mihir Kumar Mahata. I am faculty of this microelectronics and VLSI department.
Okay.
I have completed my PhD from IIT Kharagpur in
Okay.
2016 under
Oh, with,
Professor Dhruvesh Vishal.
oh, I see. Okay. Good to know. And then Dr. Avali Banerjee from GNIT. GNIT stands for? You can unmute your
GNIT
microphone
Guru
and
Nanak, maybe.
please state your name, affiliation and all. It's good to know. Oh, Guru Nanak Institute of Technology. Is it in Kolkata or somewhere else?
Yeah, near Kolkata, sir.
Oh, I see. And then Dr. Avali Banerjee, then Debolina Pramanik.
Devolina, introduce yourself.
Is a mic muted?
Sir, for whom?
I don't know. Debolina Pramanik is. I
Yeah.
just wanted to get to know everyone who all attended. Then,
So Devolina is one of our student,
okay.
MTech
Hello?
student in Macau.
Hello.
Yes, please. You may.
Yes.
Sir, am I audible?
Yes, you are. Yes.
Sir, myself Devolina Pramanik and I am the student of Microelectronics and VLSI Technology Department from MAKAUT University.
Okay, great. And how about Orijit Day? Okay. Thank you for
Rijit
at
Dey,
least.
you can unmute your mic.
Okay. So yeah, I'll there is some request, share my email address so you can have my email address.
Yes, sir. We will be sharing it with the.
I'll share the slides
Participants.
also. I'll share the slides in the first day that I had. Now, I think Humayun Rahman.
Sir, please send send it to Madhumita madam.
Yes, I will do that.
Yeah. Then we will circulate.
Sure. And Humayun Rahman.
Humayun Rahman, please unmute your mic.
He is unmuted now.
Sir, myself, Humayun Rahman, I am passed out 2019 from MAKAUT.
Okay, good. Then Noor Nabi Khan. Then Rudradeep Das.
Rudradeep Das, please unmute your mic. Noor Nabin Khan, please unmute your mic.
Samarjit Malik, Shantiram Nepal, Suchismita Paul, Tathagata Ghosh. Ghosh, or is it this GHOSE is Ghosh or something else?
Sir, Ghosh, it is Ghosh. I think it's some spelling mistake.
GHOSH, right? Ghosh is
Yes, sir.
actually
GHOSH.
No, actually his title is like that, GHOSE.
Oh, I have heard this last name, but so okay. This is a Bengali last name, right? GHOSE?
Yes, sir.
Okay. Because GHOSH I was familiar. I have a very good friend who's.
Yeah, actually the GHOSH is very common compared to GHOSE.
Okay. Okay. Then so Shantiram Nepal, Suchismita Paul. Okay. So I think they're kind of either their microphone is not working, or they are not. They're hesitant to share their speak up.
Sir, I think they are hesitating to speak.
Okay, so I don't know. Okay, so hopefully I'll get to see you guys when things normalize. Okay,
Yes.
so thank you all. Okay.
Yeah, thank you, sir.
Oh, thank you.
Thank you, sir.
Thank you.
Madhumita ma'am. Madhumita ma'am. Are you there, ma'am?